It's it's quite hard to describe the feeling right now, to just be able to see the faces of everyone who we've been talking to on Slack and now Discord, and submitting issues, helping us debug the code, like refining the UI, the UX, and everything. It's some of you we've known for 5 years, some of you for the past year, but it's like the journey. Yeah, it's really hard to describe, but I'm pretty sure you appreciate the experience that we're going through right now as a team. So thank you so much. I'm Haikal Pribadi. I'm the founder and CEO of Grakn Labs. That's the chief emotional officer about every little thing. But I promise I'm gonna try to paint the picture of where we come from and why Kraken exists and where we're going, relevant for everyone to understand the journey and hopefully find the inspiration to see how they can change the work that they're doing as well in their respective domains. Today, I'm going to walk you through from the whole journey, where there were different bits and pieces of this talk given at different moments to different groups of people, and I tried to stitch them up together to give a full context of how it all came together. And there are important pieces of the talk that will be further elaborated by Thomas on SQL, by Joshua on how the query language, the query engine actually works, by Casper on the reasoning, and James talking about how we're going to bridge the work that we're doing between Kraken and machine learning and KGCNs tomorrow. And so I'm going to try to put a framework on how the whole thing comes together. And yeah, I hope you enjoy the journey. Okay, so it goes a little bit far back, and there's a quote that has always stayed with me, and I think these days stayed with us at Kraken for throughout the entire journey, and carries the essence of everything that we're doing. So Alfred North Whitehead, that's the author of Principia Mathematica with Bertrand Russell, once said, "Civilization advances by extending the number of important operations we can without having to think about them," right? So hopefully, as we go through this talk, this quote comes to express itself in a lot more vivid way for us to understand the meaning of what these words actually mean in our current day and age. Now, I know, like me, I think for many of you here, some of you here have dabbled in robotics in their early days and may have found the love for computer science and computing by dabbling with engineering and mechanical engineering and robotics from a very young age. And that was definitely the story for me. And most importantly, I was working in a framework called ROS, Robot Operating System, which I also know that some of our community members are also working on that right now. The team from TNO, who will be speaking about that as well today, I think. And ROS is basically a robot operating system. I mean, that's what it stands for, but it's a framework for people to develop components of robotic systems to be able to work together in a distributed manner. So generally, all of the different components can be categorized into 4 different components. It's perception, planning, motion, and interaction. So correct me if I'm wrong here, but this is that's how I remembered ROS to be. So perception is like image processing, OpenCV, object recognition. Planning would be obstacle avoidance. Interaction would be verbal interaction or text interaction to the users that the robot is interacting with. And motion is the typical mechanics, motorics that you have to still take care of for the robot. Now, for me, it was always a huge wonder at that point. The teenage self of mine back then was always wondering, how do you actually get all of the different components to be able to actually share the information that they work with together in a centralized manner. So in ROS, the systems would be sending information from one component to another in an asynchronous way, but not necessarily centralized to one place where all of the information would be leveraging the information from other components. So for example, the objects being identified by the perception would be used to do the planning, automatically used for the interaction, feedback again into the main memory, used for calculating any kind of motion that you want to have. So the central system was always a wonder as to what it's actually made of, because like the data that you need to send in and the data that you need to send out and the data that you need to transform is really, really complex once you look at the interaction between each of these components. So I didn't find the answer back then, and so it was just left there, and I moved on. Now, several years later, well, many years later, so I was starting my master's thesis, my master's degree in Cambridge, and we were asked to take 6 courses. And I was only interested in 5 courses. I didn't know what other course to take. And so I thought, let's pick a course that would be fun and probably, won't really risk me failing the course, right? So I thought, here's a course with like nice, beautiful mathematical logics. Surely that should be easy. Okay. So it didn't actually reduce the probability of failing, but it was fun. And the course basically taught me 2 very important things that turned out to be very critical to the journey of Kraken today. But I didn't know it at that time. And the first thing was what knowledge representation was. Knowledge representation, so many of you here as engineers are familiar with the act of modeling, right? Modeling schemas, modeling your API, modeling your JSON data structure, modeling your key value pairs, modeling any kind of data domain that you need to work with, you need to create a model for it. However, a model that is logically consistent and logically interpretable by a computer to capture a knowledge domain is what a knowledge representation system is. So if you can define a set of statements that governs a model, for example, instance and sub in this example, where sub is defined to be sub x and y means x is a subset of y, and instance of a to x means a is within the subset of x, then if a computer were to interpret a model with such content, you would say Alice is if Alice is an instance of human, Alice is also a subset of Mano, right? This is an example of what a knowledge representation system is. I'm simplifying it heavily because the extent of which you can define a model or domain would go into propositional logic, formal logic, high order logic, and so on. Now, the specific part of reasoning that is always true within a knowledge representation system focuses on the ability to logically deduce another fact, another piece of information, given 2 or more premises, 2 or more statements that are believed to be true. The act of logically deducing this 3rd piece of information is what automated reasoning is about, right? And so these 2 principles of knowledge representation and automated reasoning became a critical part to our story, which I didn't really know at that point. And then fast forward again several years after graduating, I found myself working in a company, which I really loved at that point, and I was working in optimization scheduling. So typical traveling salesman problem where how do you get a product to a destination, right? But we're talking one of the clients, our clients were among the biggest transportation networks, supply chain networks, and delivery networks in the world. So we're not just taking into account how a product arrives at a destination, but also are we assigning the right trucks, the right trains, the right planes, the right people with the right availabilities, and so on, right? But then you want to when you create a plan, you want to make sure the plan fits with reality so that you don't actually create a plan for someone to drive through a region in which they don't have the license or that abides the regulation of that region, right? So suddenly you have to keep track of literally every single thing in the business before being able to create an optimization model that simply takes a product to the destination on time with the highest throughput for the company, right? So now, before we actually get to do all the fun stuff, so the fun stuff would be the linear optimization, integer programming, constraint programming, all of those fun stuff, you still need to aggregate all of these data points into one place so that once you do have a constraint model, the constraint model can consume from the entire network of data points and create a plan that is aware of all the data points, right? And that's when you find that the data set that you have to work with is way, way too complex. Way too complex. And just to be explicitly clear, an example of when I complain about data being too complex, I mean your SQL query looks like that, or like a third of your SQL query actually looks like that. And at some point you realize, okay, I'm not going to do this. I'm not going to debug this. I'm just not. I don't want to, right? So, and we decided, okay, some of us didn't want to. It was definitely the part that we didn't like about our jobs. But it really got me interested to basically look a little bit deeper. What actually makes these data set complex, right? There must be a reason. Why do we have a mismatch between the data set that we're facing in the real world today versus the tools that we have at our disposal? And so the first thing you realize is that, there are types and there are objects in this data set that are not completely all mutually exclusive from each other, right? You have type hierarchies, which means some types are subsets of other types. And also you have type hierarchies, you have hierarchies between relationships. Relationship between two things it may be reused for two other different things where the semantic of the relationship is still the same, such as employment, right? There's a part-time employment, there's a full-time employment, and all of them are relationships, right? And this was the first realization, why can't we do this kind of modeling at the database level, right? But then it didn't stop there. You start looking into all of the different kinds of relationships that you actually want to model, just starting with binary relationships. The simple unary relationship of reflexive relations, you can model this in SQL, we know that. You can't really, can you do that in key value? You can. But once you want to start modeling other things, such as if Alice is married to Bob, it doesn't mean Bob is married to Alice in normal databases. That's kind of unfair, right? If let's say London is located in the UK and UK is within Europe, which it is, as the continent, that means London is also located in the UK, right? So this is an example of a reflexive relationship where a relationship of something with itself. So a person can teach itself, for example, right? And symmetric relationships where you look from A to B, B to A, it's equivalent. And then relationships where if I tell you X is less than 7 and 7 is less than Y, you know that basically X must be less than Y, right? Without knowing what X and Y is, right? That's an example of a transitive relationship as well. Now, other kinds of relationships were ternary relationships that also existed a lot, right? What if there are three things that you need to make one relationship? Of course, you can do this with a join table, but the point is, there are these natural constructs that you need to create with artificial concepts, superficial concepts. But then you also have the notion of infinite tree relationships, where you don't yet know the number of role players that will exist in that relationship, right? One last one, nested relationships. If you want to make a relation, which is effectively assertion about a fact relating to another fact, between a relationship and an entity, you also can't model these kind of relationships easily. Now, the last piece are equivalent relationships. If you have two things that are related in different ways, how do you write it to the database? One of the ways, or both of the ways, and how do you maintain both of them, right? So what we realize is that, in basic mathematics, we've already defined all of the different kind of ways in which two things or more can relate to each other, right? But we can't actually express all of these relationships right now. And the consequence of that, once you do aggregate your data set into one pot, is that you have a highly permutative query. For example, if you have a data set, this was a very heavily simplified data set compared to what we were actually facing, a company, a charity, and a university data set, objects. And they all have, they might have an office, they might have a laboratory, they might have a warehouse, and you want to ask a simple question of which organizations have premises in the UK, right? So you don't yet know which relationship each of these types could have with one another. And actually, even worse is when any of the types on the left can match with any of the types in here and any of the types to the right, right? How would you go about writing a query to cover a pattern structure like this, right? Well, this is a very simplified permutation problem, so you're just going to have 3 to the power of 3 of permutation of the same query, right? Now, 3 to the power of 3 is manageable. All right, let's add one more, 3 to the power of 4. Is that manageable now? And with a few more variables, at which point does it become not manageable anymore, right? Now, and the paths that would actually be covered won't actually be all of them, but the model allows all of the paths to be traversed and requires you to traverse all of them to know that you've exhaustively searched for them. So the query becomes highly permutative and highly verbose, and that's why a lot of the queries, for example, in the previous slide, becomes really long. Now, moving on to OLAP queries, right? OLAP, with MapReduce, Pregel, BSP kind of algorithms, so clustered component, connected component analysis, or centrality measure, or triangle count, page rank. So these kind of cluster analysis, right? These are all straight out of textbook, graph analytics algorithms, which we've learned how to implement, but none of these algorithms are easily translatable from one model to another when you have a really, really complex model, right? And so in this example, which movies and actors are in the same network, right? And the answer would be this is the 2 groups. And of course, probably in your cluster, you won't just have 3 nodes connected to each other, but 300,000 nodes that are connected in one cluster. And the reference implementation of this, I think in Tinkerpop, which is a graph computing framework, is 200 lines of code of Java, of just pure algorithm, right? And it's actually something that is not very easy for anyone to just pick up. So we've seen that is also a problem for us when we have these really, really complex domains in the current traditional databases. But why are we still not able to handle these things? Now, if you look a little bit closer, SQL databases are not actually capturing the first normal form models that we basically had in the examples just now. They're still a lot lower level compared to what each of the modeling constructs require them to represent. You can always figure out a way to actually use the different low-level constructs in SQL to represent a level pattern that you want, but that needs to be created custom to your own design methodology. And the fact that you need to take care of that yourself is where the complexity starts trickling in. So Thomas actually will be speaking more about this today. I think his talk is at 1:30, which dives deeper into the difference between relational, model, and Grakn. If you look at NoSQL, well, there's no schema constraint. You always have a schema in every database because you have a model, right? To say NoSQL databases don't have a schema means it's if you delete the header of your Excel sheet, it no longer has a model. It still does. It's just not declared, right? And it's not enforced. And the fact that it's obviously the key value pairs and JSON structures are also constructs that are too low level to represent the previous relationship structures. Also didn't allow us to overcome our modeling challenges. Now, before you guys ask about RDF and OWL, we did consider RDF and OWL, but also subject, predicate, object was also too low level that it still only captures one directional binary relationships. And also, it's based on open world assumption for the web, which is perfect, but databases are not open world assumption, they're closed world assumption. And also, it's built for logicians, not software engineers, right? You kind of need to have a PhD in RDF and OWL technology to be able to actually be productive in it. So the summary is that current databases cannot model the level of complexity that we have in the data sets that we face. And the queries are really, really, really verbose, and there's no reusability across any of the graph analytics, right? Now, what we realize from that is merely the fact that current databases are now too low level to work with the new level of complexity that we have in this day and age, right? And so the solution to that was that when we realized, okay, if there is a language that can describe the model of your domain in a logically consistent manner, then, and also provide the higher level constructs natively, then one can create much more expressive schemas, much more expressive models in a way that computers, the database, can help you interpret them. And why do you want that? Because if the computer can interpret the model, then the computer can reason about the patterns. And if the computer can reason about the patterns, it can take a really, really complex set of patterns in one query and simplify them to one conclusion, right? And that's when it effectively clicked to me that, there is a real world practical use of knowledge representation and automated reasoning. And which at first I didn't think there was, other than just beautiful mathematics. And it sounded very similar to the reason why it was really hard for all of the different components in a robot to be able to share information across each other in a way that can be constantly transformed and reshuffled and be seen from different perspectives by different components, right? It's a very similar problem in that way. So what one of our community members, Brendan, helped us realize is that actually Grakn falls under the category of a fifth-generation query language. Because strictly by definition, a fifth-generation language would be one that enables you to declare the logic and constraints that you want the computer to satisfy rather than instructing the computer an algorithm on how to solve the problem, right? So it moves one higher level up. So we went on to try to model a language that would cover this, right? So this is the essence of Grakn's knowledge model, but we're not going to try to decipher screen right now. But I just want to point out some of the terms that some of you may already find to be familiar, right? There's entity, attribute, relations. Yes, they mean the same things as the ones you know about in relational databases and other databases, right? However, there's also the concept of role, and this is actually not something that we newly introduced. It's something that Chen, the author of the ER model, has already introduced, and we're going to get to see how we use more of that. And thing is merely a super type of everything that exists in the database. Now, let's see how this language actually gets used, right? So this is the first Grakn snippet for some of you, probably, to see. So let's say we want to model something simple. A company and a person related to an employment relationship, right? In Grakn, you'll define person subentity, company subentity, employment subrelation, right? And a company plays the role employee, and person plays the role employee, a company plays the role employer, right? That's where roles are being used. And here we say employment relates employee and employment relates employer. As simple as that. And you'll notice something special here where attributes are declared independently as well, but being used within these entities, which means a company with the name Bob and a person with the name Bob will be connected through the same node representing the name Bob, right? So an attribute value, as defined in first normal form, needs to sit uniquely within its own domain space, right? Name as a type is a domain space. The value Bob within that domain space should be unique, and anything else that is connected to the name Bob should be connected to the same reference. Now, let's say we want to extend the model a little bit and say we want to have more types in this database without having to change the previous types we've declared, right? We want to say there's a customer type and a startup type. And a customer is a subtype of a person, and startup is a subtype of a company. What does this mean in terms of the relationships that startups and company can play? Startups and customer. And probably you've already expected this, that it inherits the behavior from the supertypes, just like what we already know in OOP and languages like Java, which probably many of you are familiar with, right? And as you can expect here, that startup should be able to play the role in an employment relationship, play the role as an employer, and customer can play the role as an employee, right? So let's extend the model a little bit and forget about the code, right? Let's say a person can play the role of a wife and a husband in a marriage relationship, right? That we can start inserting data into the database that says a company, IBM, and a person, Alice, is in an employment relationship. Is that allowed? Yes, because we've declared that in the schema. And a startup employs a customer. Is that allowed? Yes, because it's also implicitly declared in the schema. You can derive that from the schema. A startup can employ a customer. And then a person and a customer is married to each other. Also allowed because you can derive that from the schema. Now, if you were to say something like a person being married to a company, given the schema that we had, right? We're not being judgmental, just in this example, you can't be married to a company in the schema. So when you insert this data and say commit, it will fail, right? Schema constraints are a thing again now, at least in our world again now. But the schema constraints aren't just validated against the syntactic definition in the, that was initially declared, but it's evaluated against a logical verification, right? If we can derive, if we cannot derive this pattern to be valid in any possible logical interpretation of the schema, only then it is invalidated, right? And so we're not only we're bringing schema constraints back, we're taking it one level higher to a logical evaluation rather than just a direct one-for-one based on the syntactic declaration. Now, let's start looking into like all of the other relationship constructs that we've modeled in the beginning, right? How would you model a simple reflexive relationship? Well, you would just say X and X is within one relationship again, right? So one entity can play two different roles in the same relationship, right? And it becomes a unary/reflexive relationship, right? Two players play the same role, then it becomes a symmetric relationship. This is where the power of the roles being used in the relationship comes to light, because how you use the roles in the relationship and how you have the entities relating to the roles covers the different kinds of model that you want to express, right? Let's say you want to have three entities related into one relationship. Let's say a movie, a person, and a company. And in this case, if you take if you want to attach a relationship, for example, billing ID in a movie cast list, you actually need to attach it to a relationship that connects all three of them in one atomic relationship. And given that there are movies with two actors being played by the same person, two actors playing the same character, or sometimes one actor playing two different characters, there's no way for you to uniquely represent a ternary relationship other than actually creating one relationship that connects all three of them at the same time, rather than three binary relationship. And if you want to have an arbitrary number of role players, arbitrary number of entities playing a role, then you would just declare it as many as you like, right? So as you can see, there's no cardinality constraints yet on the roles being played in Kraken. That is part of something that we want to add to the language this year, right? But we started with the most expressive version, and from here we can basically pull back on the expressivity by putting constraints into the cardinality of the relationships, right? So you can't do that yet, but we will be able to restrict the number of times you can play owner. But right now, that means you can play a role an arbitrary number of times within a relationship. Now, how would you do a nested relationship? You would take a variable that pointing to that relationship and just put it in another one. As simple as that, right? So there's almost nothing that you can't relate to other things in Kraken, in a simple construct, without having to think about left joins, right joins, union joins, inner joins, outer joins, or creating double directions of edges to cover relationship that mean the same thing from both directions. It's all natively modeled into the language, right? Now, we skip transitive relationships, where we wanted to assert that London is still in Europe, the continent. Here is where we start using rules, right? You would declare how other relationships in the database, in the model, would be related to other relationships, right? In this case, a transitive relationship between two locations, three locations. So if X is located in Y, Y is located in Z, that means X must be located in Z. And whatever direction this will occur in the database, whatever variables involved in each of these roles will be interpretable by the machine. If there are different types that are allowed to play the roles in these relationships, then it won't be constrained, right? And so this rule is as generic as you would logically interpret it to be. Now, moving on to the equivalent relationships, how would you actually treat two different relationships that are equal? Which one of the relationships should you insert? Well, you don't need to think about that if, again, you can define a rule that defines the equivalence between these two relationships. And of course, in this case, it's directional, where if a parent has two children, that means those two children are siblings of each other, right? But the reverse of that is not necessarily true, right? Now, moving on to the reasoning query, how would we have gone about trying to query a pattern like this in Grakn? This is where we would start using type inheritance, because you can see that you should have a supertype for all these types, which would be organization, a supertype for all these types, which would be, let's say, premises, and a transitive relationship rule between locations, right? So in Grakn, a query like this would be as simple as these 5 lines from 2 to 6, right? This OR is our organization, will infer all of the different types of organization. PR is a premise, will infer all the different types of premises. And once you query the relationship, will infer every combination that is valid within the database, rather than covering the entire search space, right? And then this one would infer the locations using the rules as well. So every query would natively infer all of the types and relationships at every time you query any pattern into Grakn, right? And that's how we managed to collapse something like this into something like this, right? And Thomas is actually going to show you how the modeling of this becomes this in the talk of SQL into Grakn later today. Now, the delta between what you have to write here and what is not written there are the number of important operations that you no longer need to think about. That's the delta. And if you keep on doing that, and where you never will have to look back to figure out how to write this, then you can move on to work on higher level, more complicated, more complex, more challenging problems. So, not to forget the analytics part. How would we go about solving connected components algorithms? Now, the beauty of having a really, really well-defined schema is that now we can create BSP algorithms that are truly generic to any model, any domain, any schema that you have, and is parameterizable. It's parameterizable by the types in the schema that you want to restrict the algorithm to. So you may have a very expressive domain, but you may want to just run the clustering algorithm on movies, casts, and people, right? So in Grakn, you would have a one-liner to do an entire Pregel algorithm that says compute cluster in, these are the types that you want to restrict the algorithm to perform in the database using connected component algorithm. There's only 2 algorithms right now for clustering, and I think the other one is K-core. Now, how valuable is this individual algorithm alone? Alone, probably not, but if you compile it together with the rest of the Pregel and BSP algorithms that we all use if you're doing any kind of like network analysis, then we'd imagine that it's something that it could be really, really powerful to have anyone can just perform the analysis as they think of the question rather than having to think of how to implement a MapReduce algorithm for the min distribution, how to implement a clustering algorithm to find the connected components, right? Now, there's more to come on things like page rank, triangle count, density, measures, clicks, and these are all, again, straight out of textbook, Pregel or MapReduce analytics algorithms. Now, I put a badge there, experimental, in the sense that the algorithm is, I don't know, it's already a message passing Pregel algorithm, which means it's inherently made to scale with the infrastructure. But what we haven't yet worked on is making sure the Spark infrastructure that this language is built on under the hood is as robust as possible when you scale the infrastructure. So if any one of you guys want to help us test it and scale this part of the language, we'd be more than happy to collaborate with you. So there you have it. If you put them together, you have a knowledge schema. Oh, good. You have automated reasoning in the OLTP, and you have an OLAP language, right? None of which requires you to understand how to do logical reasoning or how to write BSP, Pregel, MapReduce algorithms, or how to define logically consistent schemas. You just need to define the schema, and the database tells you if it's not consistent, right? We've created one huge layer of abstraction that takes care of all of the low-level modeling constructs and logical reasoning constructs and wrap that all up into one language, which is what we consider to be a knowledge base. A knowledge base as defined theoretically in the field, which is a system that is capable of storing complex set of information in a logically consistent way with the ability to derive new facts, right? That's what we consider a knowledge base, which is the other definition to an FAQ page, which people use the word knowledge base for. We don't mean that one. Now, people also refer to us as a knowledge graph. That's also the more trendy marketing term that people use these days, which we're not against. But a knowledge graph, in this case, would be a specific instance of a knowledge base, which is a knowledge base in the form of a graph. Now, I do want to highlight, throughout the entire conversation that we've had just now, we have not mentioned the word vertices and edges, or heads or tails, right? So we have not used any graph terminology. Now, of course, if you connect everything, everything looks like a graph, but so does your Excel sheet. But doesn't make your Excel sheet a graph database, right? But the point is that we haven't used any graph terminology, not in the language, not in the data structure. Yes, we have a lot of that under the hood. So effectively, there's a strong distinction on how you should think about using Kraken versus using other graph languages and graph databases. But the term is a knowledge graph, but not to be mistaken with a graph database. So, where do we stand right now, right? We were founded in 2015. Now it's 2020. We also can't believe how fast time flies. Now, the first year we spent just like prototyping the core database as to whether we could actually build a system of this nature. We didn't actually consider it a database in the first year. We knew it needed to be a knowledge representation system that reasons, but we thought it was going to be the core part of a semantic search engine. It was going to be some form of knowledge engine somehow, right? But since then, we've managed to refine the schema to make sure it's as reliable and as robust as possible as a language, and as expressive as it can, that we need to get it to at this point. We've iterated significantly on the query language itself, making sure you can query for every kind of pattern that the schema would allow you to exist in the database in a non-verbose and as simple as possible. We've refined and iterated the reasoner to be able to derive the conclusions that we expected to derive, and I think we've come a long way there. We've rebuilt the architecture, because when we were focusing on the first three things, we didn't really think about architecture, and it all became one big blob of mess. But now, we've rewritten it to be a proper, an architecture that can scale with the development, in the sense that now we have a proper distributed server as a backend and a client-server architecture that allows us to have multi-language clients, which at this point we've started with Java, Python, and Node.js, but we're expecting to to add more to the family of languages in the clients. And then we've moved on to building the build infrastructure, making sure that we can automate like jobs across multi-repos all the way from static analysis to unit tests, integration tests, assembly tests, distribution tests, to benchmarking, tracing, release deployment, end-to-end. And we've been putting a lot of hard work into this. Probably some of you who are working, who are in Slack or Discord for the past half year realize that the word Grabble being thrown around here and there. Grabble is the build system that we're building, which probably we're going to share with you all over the next coming year. Grabble stands for Grakn's Builder. It was at first Grakn's Butler, but it doesn't sound strong enough. So we changed it to Grakn's Builder. Now, next, what we're currently focusing on now with some of you in this room who are helping us to really, really stress test Kraken, which we really, really appreciate, is that we're focusing on rewriting Kraken for the query throughput and execution. And we're really, really excited to be sharing the results this July. We expect big changes and big announcements that we can share with all of you. And that's where we stand right now as a focus in the team. And after this, we're going to get on to working on the analytics again, making sure that the OLAP infrastructure is as robust as it needs to be, right? Now, all the while, all of you guys have built a lot of crazy things which most of us haven't even imagined yet, didn't even have the time to think about all the things you could do with Kraken. Now, I wanted to start mentioning some of them and telling you what they did with Kraken, but I suppose this is what the conference is for, right? So you get the whole day of today and tomorrow to find out what all of these people are doing and building on top of Kraken and really understand the application of the technology that we've built. However, I don't want to stop right here to paint, and I'd like to paint the future as to where I believe all of us together are moving towards. And the commonality, I think, the underlying theory that all of the companies that you're seeing here right now, including us, share under the hood. And that's, and to understand the direction is to understand where we see the knowledge-based and knowledge graph technology is moving towards in the future, right? But to understand the direction that we're going towards in the future, actually we have to go all the way back to the first time artificial intelligence was actually tried to be coined formally, and that was actually by Alan Turing in the 1950s, where he already declared that for any technology to pass a Turing test, which at that point he was referring to any AI to be taken serious as legit, basically, they needed to possess 4 different components of artificial intelligence. Turing listed natural language processing, knowledge representation, automated reasoning, and machine learning, right? And many of you probably find this book to be the university textbook that most of us loved and held dear to our hearts every night, or hated it, depending on if you're a person glass half full or empty. But it was basically straight up in the introduction of this book that Peter Norvig declared that this was one of the concepts that Turing introduced to the world. Now, if we look a little bit deeper as to how these 4 things come together, right? Knowledge representation, automated reasoning. One conceptualizes memory, the other one reasons over it, and natural language processing comprehends and produces language over the information that it reasons, and machine learning as a system to judge and evaluate to new environments, new data, and create new inferences out of the new data points about the environment. And plus one more here, which is knowledge acquisition, because I don't think, well, at least Turing didn't envisage the web as big as it is today back then. But now there's also the component of knowledge acquisition where we have too much data for us to input ourselves, where we would have systems that would automatically extract entities and extract statements out of unstructured data. And that would be the knowledge acquisition systems, right? Now, if you look at these two components, which we've been talking about throughout this whole talk, is that if you put them together, we get a knowledge base, as we've just explained. And if you replace the structure and try to place all of the different kind of artificial intelligence framework that we use in the day-to-day these days, you can start seeing a pattern. Now, of course, there are more logos here than I can afford to look up and crop last night at midnight. So I just took the two ones that I knew everyone would know, but I don't want to be discriminating against all of the other ones that are also big. I just didn't find the nice font for them. There's a lot of them here, and there's a lot of them here as well in NLP. And now there's also knowledge acquisition on how you extract data and entities from unstructured data. But you don't see much or any company that actually focuses on building the knowledge-based, knowledge representation infrastructure, right? And this gap, very much like the gap that I saw initially in a robotics framework, I think is the gap that Kraken's truly meant to be filling, right? Now, tomorrow, James will be talking, like, in the keynote, diving deep into how these two things can start to be bridged through KGLib and KGCN. But ultimately, the way we see where Kraken and any knowledge-based technology going towards in the future is as a unified knowledge representation system, a unified language to represent knowledge across all intelligent systems infrastructure, right? Not to do the learning, not to do the speaking, not to do the NLP, not to do the entity extraction, but how do you represent all of them in a way that all of the systems around the database can logically interpret and share and transform information across one another in a universal way, in a logical way. And all of the principles that will be involved in trying to engineer this system that talks to every other component of intelligence within the architecture is the set of principles of knowledge engineering. That term was not the first time to be coined now. It's a study that has been, albeit niche, but quite old in the field, which is the study of how to engineer knowledge-based systems in general. But over the coming year, and definitely in Grakn Cosmos next year, our goal is to lead the way in trying to share what we believe the principles that are important in knowledge engineering to bring together all of the different components of intelligent systems to work under one language, and what that engineering architecture should look like, and what the design patterns should look like, what are the modeling and engineering techniques should look like. But for now, I leave it there. I hope you guys will find meaning and inspiration from the talks that you'll find over the next coming 2 days. And I hope I'll see more of you throughout this journey that we're going to go. Thank you.